So the title is, mapping cold gas in the galaxy with sodium D, with a lot of instruments, including DESI, VLA, MMT. And of course, this work is in collaboration with a lot of people, both in this room, Eric Koch, Theo O'Neill, Charlie Conroy, Scott Lukin, Lars Rehnquist, and maybe also you after this week. So let's get started. I know we were told not to put this up, but I have to. So why cold gas? There are two components to my title, right? There's the cold gas part and then there's the galaxy part. So cold gas, in the form of sodium D, is readily accessible in optical telescopes that are ground-based. That's a lot cheaper than UV telescopes in space, right? So that's one motivation. But why the galaxy? So the galaxy probably is chock full of cold gas across, every aspect of its baryonic cycle. But we also live in it. So since we live in it, we can probably study it through millions of lines of sight. And in the case for the DESI instrument, it really is millions of lines of sight. So as of 2023, we've collected something like 30 million galaxy, quasar, and stellar spectra through millions of lines of sight. I won't go into too much detail about what DESI is because we just have 10 minutes. But let me just throw up what an example spectrum could look like. So on the bottom panel is an actual galaxy spectrum in gray. In the red line is showing you the best fit model. It's a bespoke galaxy model for DESI. And then what I'm proposing to do is taking this tiny little sliver of pixels and blow it up and try to measure sodium absorption. So it's around 5890 angstroms, and then the black dots are indicating the gray line divided by the red line, right? So the data divided by the model. And as you can see, most of the dots are up at 1, which is great. Model equals data. But there are two very conspicuous Gaussian absorptions that you can see. And this is precisely the sodium D doublet, our favorite 5890, 5096 resonant doublet line that has an ionization energy of about 5 electron volts. So whenever I find galaxies like this, I run an entire Bayesian search for the best fit parameters for the separation. Actually, the separation is fixed. That's the one thing I don't search. The location, the line widths, the line ratios, and amplitude. And the Bayesian part is really important because when you have a lot of galaxies, right, sometimes your residuals are actually better fit by two pairs of Gaussians, not even a single one. And sometimes no Gaussian is better than one. So for all these scenarios, I run different fits. I make some automated way to make a decision as to what the best fit is. In this case, it's the Bayesian information criteria, and then do that over the entire 30 million spectra. Lastly, if along some lines of sight, we just don't have that many bright galaxies, in this case, this is around 20 galaxies. They're all at around SNR of like 3. Then you can median stack in order to be able to still recover some sodium absorption despite one single target not having a strong absorption feature. So if you do that over the whole sky, or rather 2/3 of the sky, or 1/3 of the sky, this is what you get. The gigantic hole in the middle, that's the southern hemisphere, because DESI is in the north. We're now looking at this from a galactocentric coordinate. So x-axis is longitude, y-axis is latitude. And the colors are indicating sort of the strength of the absorption. And you can just flicker it back and forth between H1 emission and sodium absorption, and they're quite similar. But let's zoom in, right? So this is just a random patch of 20 by 20 degree patch of the sky at around longitude of 40 degrees, latitude of 40 degrees. Far left panel is showing you what the sodium absorption is looking like. It looks a lot better on my laptop when it's not projected. The third panel is showing you the H1 emission. The middle panel is showing you the composite color, fake color image. And on the very right panel is showing you the locations of each and every one of galaxy that went into this measurement. This panel on the right is actually restricted to high signal-to-noise ratio and bright galaxies. So one of these targets can give you a reliable sodium column density measurement. So here's what I'm taking out of it. If you compare the sodium and the H1, to first order, they're quite similar, right? There's a bunch of stuff on the bottom right corner. There's a bunch of stuff in the bottom right corner. Oh, the laser pointer works. Oof. And there's some notable cavities that are shared by both features. And when you overlay the two on top of each other, right? Purple means there's both sodium and H1. Blue means there's just sodium. Red means just H1. You can really see that the sodium is sort of picking out the knotty, dense clumps in H1. And this drives well with the expectation that we think sodium is strictly probing the cold neutral medium, while as H1 is a combination of the warm stuff, so around 10 to the 4 Kelvin, and the cool stuff at around 100 Kelvin. So it works well, at least with what we expect. So this is all nice. Most of it is going to be the local interstellar medium, likely. But what about the circumgalactic medium, right? So of course, with H1 emission, we don't have distances, so it's hard to tell what's from the CGM or the ISM. But one thing with certain that we know are these high velocity clouds are not from the local ISM. Maybe it's the distance ISM, but it's certainly not the local 2 kpc ISM. So if you zoom into parts of the high velocity cloud map where we have sodium detection, we see something like this. So these are 4 examples in which in the center I have indicated where the sodium absorption is in a star mark. And I've colored the sodium star with the color of the velocity. So the stars are not transparent, although they look transparent. And they look transparent because they're at the same exact velocity as the underlying H1. So in this case, there's the M81 group, which is the map that Eric showed earlier. It's complex C, the Wannier clouds, the Anderson shell, and we basically find sodium absorption in all the major high velocity clouds that we know of. A quick detour. I wanted to talk about sodium abundance, sodium D1 abundance. So there's this classic result from Merger et al. 2015, which is this black dots down here, which is that they find that the sodium D1 column density over H1 column density, so sodium D1 abundance, is constant as a function of H1. But actually, in my map, I find the exact opposite, which is where there's a strong, tight correlation, a negative one, between the sodium column densities, sodium abundances, and H1 column density. But when I sort of smooth my map at the same angular resolution to which Merger et al. Had access to, you get something that looks like a flat line. So my proposal is that the sodium abundance actually does increase towards lower H1 column densities. It's just a manifestation of your data, of your angular resolution. And this trend makes physical sense to me because if you think about the H1 emission, right, it's warm, a lot of it is warm. And where you have cold, dense neutral medium, that is small angular resolution, is going to be smoothed out by your H1 beam. So it makes sense that towards those dense clouds, we have higher sodium column densities compared to what you might expect from H1 emission. Enough of that. So we have this fun VLA program where we go and target some of these interesting high velocity pixels from the sodium map. This is done with work with Eric Koch and Theo O'Neill. This is the M81 group. and we do actually, for a lot of the cases, have positive detections of indeed cold clumpy stuff. So the million-dollar question is, right, like what are these cold clumpy stuff? Is it turbulent boundaries or is it cold condensation? That's for the crowd to decide. But the general strategy is the following. We kind of want to image the HVC boundary layers conditioned on the sodium because you want there to be dense stuff so that you can actually image it. And I want to be able to observe sort of the small scale at which you can see fragmentation occur out in real nature, right? Because there's a lot of these simulations that predict sort of cascading fragmentation down to infinite scales under your resolution limit. But that probably isn't happening in our galaxy. So this is an example of an actual HVC. It's a Cohen stream. It's in our galaxy. It's about 10 kpc away, which means that our beam size of an arc minute is around 3 parsecs. And here, this whole thing is about 10 arc minutes long. So it's about 10 resolution elements in a row. And we just don't see significantly over and under dense clumps forming within this subclump. So this is an example of what we might be able to do. The Cohen stream in particular is an interesting one because it's a low metallicity infalling cloud. So the cooling properties there are going to be different, which might inform whether or not it can fragment. All right, so in the last minute, I'm going to talk about stars. What about them? So fortunately at the CFA, we have folks like Phil Cargyle who are experts in modeling stellar atmospheres. And we're able to do the same exercise, but with stellar spectra instead of just galaxies. This is an example, high resolution or mid resolution, depending where you come from, stellar spectrum, where the blue line is indicating where the stellar contribution is, and then the rest of the doublets are intervening material. The advantage of stars is that you have distances. So what we have proposed and gotten time, and we'll do this semester, is basically map out a bunch of the classical HVCs with a lot of stars ranging from 0 to 50 plus kpc, with some quasars in the infinite background, and try to obtain distances to these things. Oh, and I just wanted to make sure, no high velocity cloud is safe. We will measure distances to every one of them. All right, so here's my TLDR. It is possible to map absorption like emission. You can do it contiguously if you have enough spectra. Sodium D is everywhere, including CGM structures. It visually seems like it does trace CNM. And the VLA does confirm cold clumps where we have sodium absorption. We're going to extend this analysis to stars, and I'm on the job market. So please look out for the application. Thank you.
Okay, we have time for questions. Here first.
So, very nice talk. I'm curious about if you have accounted for beam sparing when you do your sodium to H1 plot, abundance plot. Simply because, especially at low H1 columns, your beam sparing effects would be far worse than the high ones.
Yeah.
And that might be a reason why you might see some biases.
No, I think you're absolutely right. And that's kind of what I'm claiming as well. So at towards the low H1.
So even the beam sizes you have, you might have beam sparing effects in your analysis. That's what I was thinking.
Oh, I see. Let's chat offline about that.
What's your resolution on DESI?
Spectral resolution
Yeah.
ranges from 3,000 to 5,000. Around the sodium area, it's around 4,500.
What do you derive column densities derived from resolution?
Oh, so you derive it very coarsely. So you can get a column density of just the D1 and then the D2, and then you just cross your fingers and hope that it's not insanely saturated. But the error bars are on the order of plus or minus 30% of the column density. So we're not claiming to do exact column density measurements with DESI. With high resolution spectra, with this, I think you totally can.
What's your resolution here?
This is 30,000.
Yeah. I will show you some spectrum taking at 180,000 resolution, and that can be saturated even with a resolution of 30,000. They will not be saturated. So.
Sure.
But that will affect your column density. That's what I'm asking about.
Yeah, absolutely. But it'll affect it at on the order of itself, not on the order of factor of 10.
Not sure.
Yeah, we can chat offline.
Okay. And question here, maybe the next speaker could sing a bit and then start getting set up.
Love it.
So, Jesse, I'm interested in the coherence between nearby sightline pairs.
Yeah.
So have you looked at a statistic like delta equivalent width as a function of separation? And how does it look? And can we use something like that to think about constraining the size scales of clouds?
I've tried to do that for the sodium map. I have like a map of basically like a power spectrum really,
Yeah.
but I'm not sure what to do with it.
Me either.
Yeah. Thank you.
Good.
Okay, let's thank the speaker again then.